the first 26 cards in this nicely randomized deck. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. Set this aside. Set this aside. I'm going to lay out 3 cards. Oh.
Yeah.
I'll stack this together so
Yeah, result the camera.
1, 2, 3 cards. Okay. And I'm going to complete them up to 10. So this one's already at 10. If you can see, it's a 10. So I'll leave that one alone. 9, 10, and then 3, 4, 5, 6, 7, 8, 9, 10. Now I'm going to count them. 10 plus 9 is 19, plus 3 is 22. So the 22nd card in this deck is the Queen of Hearts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Queen of Hearts. It's a good trick. Come on. It's actually not magic at all. I learned it from a guy in a pub in London outside of Hyde Park. He was showing us it, and it took me like 4 or 5 times watching him do it, but I figured it out. So I'm not going to tell you, but any of you can figure it out. I've had students in the past figure it out. So it's on video now, so you can always, look at it, I suppose, and watch as many times you want to figure it out if you want to. Okay, so let's take a look at this one here. So this one again has been shifted 2 to the right. So again, I'm going to do over 1, up 1, over 4, 1, 2, 3, 4, up 2, and then over 9, up 3. And like Jenna had pointed out, if you're shifting right 2, that means my x's all go up 2. So if I look at my original one here, the y's stay the same, 0, 1, 2, 3, but my x's go up 2 because I'm shifting the x's up 2. So 0 becomes 2, 1 becomes 3, 4 becomes 6, 9 becomes 11. So those are my new points.
What do you mean x's go up 3?
I'm shifting 2, sorry, to go up 2. Because I've shifted right 2.
Oh, the original spot.
From the original. So from the original, this is my original graph.
Oh.
Right, from my original.
Okay.
Okay, so then I'm going to, for the inverse, I'm going to swap them. So 2, 0 becomes 0, 2, 3, 1 becomes 1, 3, 6, 2 becomes 2, 6, 11, 3 becomes 3, 11. And then I'm going to graph those new ones. So 0, 2, 1, 3, 2, 6, and 3, 11, which is somewhere way up here. So it's going to look something like that. The original one was something like this. Yeah? Great. What's the domain of the original function? Let's see, it starts at 2 and goes off to infinity. So 2 to infinity. The range is from 0 to infinity. Starts at 0, goes up to infinity. And you'll notice that these swap places. So then for my domain, the domain is 0 to infinity, and the range, it starts off at 2 and goes up, so it goes 2 to infinity. So you can see how the domain became the range, and the range became the domain. On the next page, let's see here. Oh, this isn't the way, isn't it? If I can get it to do it again. There. All right, so here we have, I'm going to draw it, and I'm going to do Janet, Callie's trick of like kind of knowing that she's like, oh, I know it's going to be sort of mostly in the positive hemisphere, so she's kind of doing it kind of low like that, which is much nicer. And here we've shifted up 3. Right, so instead of being at 0, 0, I'm starting off at up 3. I'm going to go over 1, up 1, over 4, up 2, over 9, up 3. There's my original. I shifted one. And these points are, let's see, 0, 3. And then again from I look at kind of my original, what my original one was before. It was 0, 0, 1, 1, 4, 2, and 9, 3. So for these ones, my x's, if I shift up 3, my x's stay the same, 0, 1, 4, 9. But my y's will all go up 3. So they become 3 more. 0 becomes 3, 1 becomes 4, 2 becomes 5, 9 becomes 6. Kind of the easier way of doing it. I thought that was nifty. And then in my inverse, they all swap places. So it goes 0, 3 becomes 3, 0, 1, 4 becomes 4, 1, 4, 5 becomes 5, 4, and 9, 6 becomes 6, 9. So I'm going to graph those points. 3, 0, 4, 1, 5, 4, and 6, 9. Here, so then that one becomes this guy like that, somewhere like that. Oh, I misgraphed that one. Oh, that's why. That looks better. And then if I do my dotted line, let me put my dotted line in there so we can see that. Put the dotted line, and then you can see how it's totally reflected across that line. Should have done that in this one too. That dotted line in there. Oh, I did. Okay, good. Okay. Now, my domain of the original graph, 0 to infinity. And my range is from, starts at 3 and it goes up to infinity, so 3 to infinity. And then the domain, because my range is 3 to infinity. Let's double check that. Let's see, yep, 3 and not to infinity. And then my range goes from 0 up, 0 to infinity, which totally makes sense, right? Because this one goes there, yep, that's the same, and this one becomes that one, totally. All right, great. So now, we're going to move on to the next handout, which is the first one of Unit 5. First one is Unit 5. There you go. Quadratic functions, yep.
Sounds scary.
Yeah, it sounds scary, but really it's super, super, super cool. This is the niftiest class because I remember tutoring in the math lab and finding out that I always thought to find the minimum or maximum of any function you had to use calculus and take the derivative. But as it turns out, with quadratics, you can just use this super cool way and find the minimum and the maximum just with algebra. It's so neat. So it's actually kind of really, really cool. So first of all, a quadratic function, it has a cool name, quadratic function. It's any function of the form where your x is squared. You have an x squared in there. So the standard form is ax squared plus bx plus c, where a, b, and c are just some number. But a can't be 0, because if it was 0, it would just be linear, right? It wouldn't have an x squared. So, so it's ax squared plus bx plus c, where a, b, and c are what we call the coefficients, the numbers in front of the variables. Basic one is just x squared. F of x equals x squared, so y equals x squared. The graph of it is called a parabola, right? So all quadratic functions have a graph of the shape person's ever seen a parabola before? You've all. You haven't seen, yeah, I haven't seen a parabola before, right? Good, it's just a little U thing. What is the domain? All right, so the domain, let me ask you this. What's the two things you can never, ever, ever do?
Divide by 0.
Divide by 0, right? Can never, ever, ever divide by 0. Yes?
Square root of a negative number.
And you can't take the square root of a negative number. Here, we have y equals x squared. Are we dividing by x? Do we have something where dividing and x is in the denominator? No. Ryan's like, no. No. Are we taking a square root of something with x inside the square root?
Yes.
Square root, not square, square root.
Oh, square root. I don't know.
No, there's no square root. So, x can be anything. Does that make sense? It doesn't, the only time that there's a restriction on x is if we are trying to divide with something, by something with x in it, or if we're taking a square root and x is in the square root somewhere. Does that make sense? Otherwise, x can be all real numbers. My domain is all real numbers. So negative infinity to positive infinity. Now the range is a different animal. What's up with the range? What's the lowest this thing goes?
0.
0. Does everyone agree with that statement? Lowest it goes is 0. You can touch 0. What's the highest it goes? Infinity. Good. Perfect. The point where it turns, see where it goes down and turns around? This right here is called the vertex. Vertex. The basic vertex is at, for my basic function, my kind of my most common, like my starting point case, right? Like, you know, like is 0, 0. Just like with the swoosh, with the square root, or the s with the cube root. It all centers around this one. This one, same thing. It kind of centers around 0, 0, 0, my origin. The vertex is the lowest point in the graph, called the minimum. Because remember, x is my input, y is my output. So my output is the height. What's the lowest it ever goes? 0, 0. That's the minimum. My y is kind of what I care about. That's what my result is, what my answer is. Good. All right, so it's the minimum value of the function. It's the minimum output of the function. All other quadratic functions are changed by transforming this one. So remember, this is ax squared plus bx y equals plus c. So this guy tells you how much you're stretching it. Sorry, how wide is it? Wide it is. If it's getting stretched or not. So it determines kind of the width. If it gets stretched a lot, then its width becomes really skinny. If it's gets squashed down, then it kind of becomes wider. What happens to reflect it across? So B and C kind of determine kind of where it gets shifted. We'll get into that later. What happens to reflect the graph in the y-axis? So let's reflect it in the y-axis.
Nothing happens.
Nothing happens. Oh, great. Great. So if I reflect in the y-axis, this point goes over here, this point goes over there, this point goes over here, that point goes over there. It's itself. Does that make sense? So if I reflect across the y-axis, it's itself. If I reflect it across the x-axis, what about that? This point goes here, this point goes here, this point goes there, this point goes here, this point goes there, and it looks like this. Right?
Mm-hmm.
Everyone on board with that part? Has everyone done it on theirs?
Who wants to draw it in?
Yeah, draw it in.
Okay.
Okay, so so here, if we reflect on the y-axis, it stays the same graph. Reflect the graph on the x-axis. What's the symbolic expression for the reflected function? Aha. So let's see. Here, my x's stay the same. X's are the same. Y becomes negative y. So that means that, let's see, y becomes negative y. So that means that I have negative y equals x squared, which becomes y equals negative x squared. There's my function. Does that make sense for folks? As I fall out of the chair. So here, as I rotate from this point to that point, the x's stay the same, the y's become negative y's. So we can see that. I go from that point to that point. So here, the y's become negative y's, the x's stay the same. So my function, y equals x squared, the y becomes negative y. So how do I get rid of this? Multiply both sides by negative 1. So y equals x squared.
So this one is, the left one is the domain and the right one's the range?
What? Neither of these are domain and range. This is the function.
Oh, we're not doing that. Okay.
So the domain and range we're going to do next.
Okay.
Right, this is an equation. Y equals something with x in it. This is an equation.
Okay.
Domain and range is the interval thing. So what's the domain? What's my domain? Am I dividing by x or taking the square root of x? Or anything with x in it? It's not a rhetorical question. Am I dividing by anything with x in it? No. Am I taking a square root that has x inside? No. So this is my domain's going to be all real numbers. Is everyone on board with that? What's my range? What's the highest it goes? Highest this goes?
0.
0. Lowest it goes?
Negative infinity.
Yep. 0 to negative infinity.
Oh, wouldn't it be negative infinity to 0?
Oh, I'm so, yes, it would be. That's awesome. I love that. Negative infinity to 0. Perfect. My symbolic equation was y equals negative x squared. Okay, when the graph is reflected, the vertex becomes the highest point. That's the maximum, right? So in the red one, 0, 0 would be the maximum. Everyone see that? It's the highest it goes. All right, so these are not scary, right? These are reasonable. No scarier than anything we've had so far. Everybody feeling okay with these so far? Yeah, piece of cake.
I gotta go back to this because I didn't get it. The symbolic expression, you put two different expressions, so I don't know which one was the answer.
Negative y equals x squared isn't, I gotta solve for y. So it becomes y, if you multiply both sides. So the equation needs to be y equals. Do you know what I'm saying? Eric?
Okay.
It needs to be y equals, not negative y equals. So I had to clean it up to get y by itself.
Oh, so you just like solved for it
So y becomes negative y. So I made y negative y.
Yeah.
And then I had to solve for y to make y just regular, ordinary y. So when I do that, I have to multiply both sides by negative 1, so I get this.
negative 1.
Yeah. Okay. Right, so whenever the coefficient is, this is fun. Okay, so whenever the coefficient is, make this one bigger. Oh, that's not bigger. No. Okay, whenever the coefficient is positive, and that's when your A is positive, my graph opens upwards, right? Like this previous one over here, right? A is 1, it opens upwards. So when the coefficient, so here's my x squared. It doesn't matter what's in front of the x or what's in front of the, okay, so first of all, let me ask you this. What's my A, what's my B, what's my C? A is 2. Everyone agree with that? Everyone look up. My A is 2. What's my B?
3.
It's not 3.
Negative 3.
Negative 3. So see how my B is negative 3? What's my C?
Negative 5.
Negative 5. Good? Everyone following? So here my A is positive, it opens upwards. So in other words, whenever A is positive, it's a happy face. When A is negative, people who are negative are unhappy, so it is a sad face. It opens downwards. So that's the easiest way to remember it. When A is positive people are happy. When A is negative, it's unhappy. When it's happy, there's a minimum. When it's unhappy, there's a maximum. Because it goes down and down forever, but it only goes so high. All right, so let's see if we can understand how these things affect everything. So let's do them quickly together. So let's see. F of x equals x squared. What's negative 2 squared? So negative 2 times negative 2?
4.
4. Positive 4. All right, negative times negative is positive. Negative 1 squared?
1.
1. 0 squared?
0.
1 squared? Yeah, I'll call on people. David, what's 1 squared? What's 1 times 1? 1 times 1?
1 time. Oh, just 1.
Yeah, just 1. Okay, good. Deja, what's 2 squared? 4. Yep, it's so squaring means you multiply it by itself. 2 squared is 2 times 2. 1 squared is 1 times 1. 0 squared is 0 times 0. Squaring it, you're multiplying it by itself. Negative 1 squared is negative 1 times negative 1. Negative times negative is positive. 1 times 1 is 1. Everybody feeling all right with that part?